All right, so we've been talking about radioactivity. Now we're going to talk about the uses of radioactivity. So there are several different uses: tracers, medical imaging, radiation treatment, irradiation of foodstuffs, and providing energy. So tracers are in biological and chemical systems. A radioactive isotope can be followed using the radiation it emits. It is possible to determine if there's a problem with blood flow in a patient, or a chemical or biological reaction can be watched to determine the mechanism by which it occurs. Radioactive isotopes are very easy to detect, even in small amounts. Okay, so then medical imaging. Some isotopes are used for diagnostic purposes. Thallium-201 is absorbed by healthy heart tissue, but not by damaged tissue. So a thallium scan can determine heart problems or determine the damage from a heart attack. PET scans using positron emission are used in diagnosing medical conditions such as Alzheimer's disease. So MRI involves using a magnetic field to image hydrogen atoms found in water. The hydrogen atoms absorb the magnetic radiation, similar to the electrons in the shells absorbing light radiations, providing a good picture of soft tissues which contain a lot of water. Radioactive isotopes are not used in MRI. So MRI is not, but medical imaging using PET scans is. Radiation treatment. This is used when cells need to be killed. Cancer treatment, destroying white blood cells in order to facilitate a transplant. The radiation causes damage to the DNA, so it is effective against cells which are rapidly dividing, such as cancer cells. The other cells in your body that rapidly divide are stomach cells and your hair cells. So that's why patients experience nausea and also hair loss. Okay, irradiation of foodstuffs. Radiation kills microorganisms which can cause food to spoil. There is also an interest in using it to decontaminate mail. So this is to prevent anthrax poisoning. Lastly, radioactivity can be used to provide energy. As discussed under fission, the energy given off in a nuclear reaction can be used to boil water to power a steam turbine and generate electricity. Okay, so now this brings us to half-life. So an important topic is how long it takes before a radioactive isotope, or radioisotope, decays. This is essential to know when considering how to dispose of radioactive waste or how radiation can affect us. So I like to have students visualize half-life with regard to food, because it's a lot easier to think about food instead of this unknown radioactivity. So let's say that you have two pies. One is apple and one is rhubarb. So apple pie, if you look at how it hangs around after Thanksgiving or Christmas, in about 15 minutes, 4 pieces remain. In another 15 minutes, 2 pieces remain. Another 15 minutes elapse, and only 1 piece remains. And then, you know how it goes with the last piece of pie. Everybody just nibbles off a little, and it can't be, nobody really claims that piece. Now the rhubarb pie, it takes a day for half of it to remain. Another day for a quarter. And another day for just one little slice. So what is the amount of time required for half of the pies to disappear? So the half-life of the apple pie, it's like 15 minutes. And the half-life of the rhubarb pie is 1 day. So which is better? I would say the apple. Although I like rhubarb pie. I have nothing against rhubarb pie. I think it's great. So half-life is the amount of time required for half of the sample to decay. So we're going to work some problems with half-life. And what I will say is that we will use whole numbers. I'm not going to give you like 3.75 half-lives or 3.6 half-lives. These will be whole numbers. So if you go to the next page, the half-life of nickel 63 is 92 years. If I start with 100 grams, how long do I need to wait until all I have left is 25 grams? So there are a few things. Usually students freak out because it's a word problem. I can't do chemistry, it's hard. What everybody says is true. I'm going to drop this class and I'm not going to be able to complete my life objectives. I'm not going to be able to take whatever I need to take to do what I want to do. It's not that bad. It's really not that bad. So what you need to do is start off at t equals 0. And at t equals 0, you have 100 grams. I don't care what isotope it is. It does not matter. What matters is the half-life and how much you start with and what you're trying to get to. So to figure out how many half-lives you have to undergo, each arrow represents a half-life. So the time is going to be 92 years right here. And I'm going to half this. So half of 100 is 50. Okay, so they're asking for 25 grams. So I'm going to have to go through another half-life. And my time is going to be 92 years plus 92 years. So I end up with 184 years. At 184 years, I end up with 25 grams. So this is how long it takes. Now, mistakes that students make, they forget to start at time equals 0. So they'll start at t equals 92, and then they'll only have one half-life, and they'll get the incorrect answer because they would get 92. So I always encourage students to start off at t equals 0, put your arrows, and then fill in the rest. So let's work number 2 this way. The half-life of YB175 is 4 days. If I start with 256 grams, okay, so this is something I need to know, this is something I need to know, and this is something I need to know. So if I start with 256 grams at time equals 0, how much is left after 16 days? So I'm going to have to go to 4 days, and then another half-life's elapsed, so that's t equals 8 days. Another half-life's elapsed, and that's 12 days. Another half-life, that would be 16 days. Okay, so 256. 256 divided by 2, 128. Divided by 2, 64. And divided by 2, 32. Divided by 2, 16 grams remains after 16 days. So really, it's just getting it set up and knowing what numbers you're looking for. So I want you to work 3 and 4 now on your own. Hit pause, and I'll go over them when you return. Okay, so for number 3, cover this one up so it's not too distracting. Go through a lot of half-lives, 1, 2, 3, 4, 5, 6, and you end up with 32 grams. For number 4, you end up going through 1, 2, 3 half-lives, and you get to time equals 2,700 years. So those problems, practice, do your homework problems. They're easy to make mistakes if you don't start off at time equals 0. So be sure you start off at time equals 0. Don't worry about 241. Sometimes I have students who will take 241 and they'll put that as their starting quantity. So just be sure that you label your starting quantity clearly and double check, double check, double check. Okay, the last part of Unit 1 is carbon dating, and this is a really useful thing. We've learned a lot from this. So an application of half-life is the use of the decay of radioisotopes to date ancient objects. Carbon-14 is a natural isotope of carbon, which occurs in small amounts in all living things. So when an organism dies, the carbon-14 decays. It would be replaced from food if the organism was still alive. So comparing the amount of carbon-14 in an ancient sample to the amount in a living organism gives an estimate of the time passed since the organism dies. The amount of carbon-14 normally found in an organism is small, so this dating technique can be used for objects 50,000 years old or less. You cannot date dinosaur remains from this technique. So carbon dating has been checked against tree ring counting and has been found to be accurate. Other isotopes with different half-lives are used for dating older or younger objects. For example, an isotope of lead is often used to date and authenticate 16th or 17th century paintings, because lead compounds were used to provide certain colors of oil paints. So radioactivity is definitely very useful, and you can see its applications. And that concludes Unit 1. So do all your homework problems that are listed from your textbook. There's a review, but I highly recommend doing your homework problems again and again, because what you're going to run into on the exam is problems. And if you don't know how to do the problems, you're not going to be able to complete them in the time allotted. So even though you can take them at home and you might be able to look at your notes, you're going to have to know what you're doing pretty quickly. So email me if you have questions. Get help at the SRC. Come by my office hours. I would love to see you and hear from you. Take care.